The gauge needle climbs past 180, then 200, then locks at a number the operator has never seen. He lunges for the safety valve. The handle won't budge. In the next 4 seconds, 3,000 horsepower of superheated steam tears through 6 inches of riveted iron, launching a 40-foot boiler through the brick wall like a cannonball. The blast throws men 150 feet into the rail yard. The building's 3rd floor pancakes into the machinery below, burying 23 workers under tons of twisted steel and scalding water. This is March 1905, and this is how an ordinary Tuesday becomes a mass grave. But here's what makes it worse. This wasn't an accident. Every gauge, every rivet, every safety system had been deliberately compromised to squeeze more power from a machine already pushed beyond its limits. So the question isn't whether this explosion could have been prevented. The question is, how many others saw it coming and said nothing? If stories like this move you, please like, subscribe, and tell me in the comments which industrial disasters to explore next. Your support makes these detailed investigations possible. Now, let's go back to where it all started, to the moment when American factories decided that more power mattered more than the men who made it run. The American factory floor in 1880 runs on a single, brutal truth. No steam, no money. Every loom, every lathe, every stamping press connects by belt and pulley to a central power source. For decades, that source was the water wheel, chained to rivers and seasonal flow. But the post-Civil War industrial boom demands something fiercer, something that doesn't freeze in January or dry up in August. The stationary steam boiler answers that call. These machines are architectural in scale, 30 feet long and 8 feet across, holding thousands of gallons of water heated to 200 degrees under 150 pounds of pressure per square inch. One boiler can power an entire textile mill. 2 can drive a steel foundry's rolling equipment. 3, arranged in a battery, can keep a locomotive factory running 3 shifts without pause. The economics are irresistible. Install a bigger boiler, run more machines, hire more workers, capture more market share. But the pressure, literal and financial, never releases. Factory owners face a choice. Operate at design capacity and watch competitors outpace you, or push past the red line and multiply your output. Most choose the latter. They connect boilers in series, feed them cheaper coal with higher sulfur content, and delay maintenance shutdowns that cost production time. What happens when an entire industry decides that maximum capacity isn't enough? The boiler room becomes the factory's literal and metaphorical heart, a chamber where heat, pressure, and human desperation concentrate into something unstable. The men who tend these iron giants work 12-hour shifts in temperatures that reach 120 degrees. They shovel coal into fireboxes that glow white. They watch gauges that measure forces capable of tearing steel. Their job isn't to keep the boilers safe. Their job is to keep it running, no matter what the needle says. By 1890, more than 100,000 stationary boilers operate in American factories, and the number climbs every year. Each one holds enough energy to level a city block. Each one operates under the same unspoken rule: production over caution, profit over safety, output over everything. The stage is set and the pressure is building. A boiler shell looks solid until you understand how it's made. Thousands of hand-driven rivets hold overlapping iron plates together, each one hammered hot into pre-drilled holes by men working in teams of 4. The 1890s standard calls for rivets spaced every 3 inches along a seam, overlapped in a pattern that distributes stress across the joint. Miss one hole by 1/16 of an inch, and you create a point where metal flexes unevenly under pressure. Let a rivet cool, crooked, and the seal begins to weep. Multiply these small errors across a 30-foot shell, and you've built a structure that's only as strong as its weakest connection. Let me take you to Hartford, Connecticut, in 1854. The Fales and Gray Car Works boiler explodes during a routine morning startup, killing 21 workers and injuring another 50 more. Investigators recover fragments showing rivet holes drilled off-center, allowing steam to force its way between plates. The company had accepted the boiler from the manufacturer without independent inspection. The shell was defective from the day it was installed, but rivets are only the beginning. Water chemistry attacks iron in ways most operators never see. Let water sit stagnant and oxygen begins the corrosion process, pitting the interior surface. Feed a boiler with mineral-heavy water and scale builds up, insulating the iron from the cooling effect of the water itself. The metal overheats, it softens. Under constant pressure, it begins to bulge. Inspectors in the 1890s routinely find boilers with plates worn from half an inch down to the thickness of a dime, still in daily service because shutting down means lost revenue. What does a factory owner see when he looks at these warnings? The boiler inspector from Massachusetts reports finding 347 boilers in dangerous condition during 1893 alone, with 89 ordered immediately removed from service. Yet, records show that 34 of those condemned units returned to operation within 6 months, their owners having made minimal repairs or simply moved them to facilities outside the inspector's jurisdiction. The evidence is physical and damning. Recovered boiler fragments tell stories their operators never lived to share. Cracked welds, sheared rivets, corrosion patterns that follow waterlines like rust-colored maps. These aren't mysteries. These are predictions written in metal, ignored until the moment they come true. The man who controls 3,000 horsepower rarely knows what he's controlling. Most boiler operators in the late 1800s receive no formal training. They learn from the previous shift worker, who learned from someone before him, creating chains of knowledge based on habit rather than understanding. A new hire might get 3 days of observation: how to shovel coal, how to check the water glass, how to crack the blowdown valve once per shift. What he doesn't get is instruction on metal fatigue, pressure dynamics, or the physics of steam. He's told to keep the needle in the green and the water above the red line. Everything else is feel. Let's go back to Braidwood, Illinois on February 16, 1883. The boiler at Diamond Mine explodes during the morning shift change, killing 69 miners waiting to descend. The operator had noticed the pressure gauge climbing, but assumed it was temporary, a pattern he'd seen before during cold snaps when demand spiked. He didn't know the safety valve had frozen shut overnight. He had no training to recognize the danger. The inquest records his testimony. "I thought it would settle down like it always does." But how do you measure the weight of responsibility placed on men who can't read the gauges accurately? Survivor accounts describe the impossible calculus. If you shut down for suspicious noises, you're labeled overcautious and risk termination. If you push through and something fails, you're blamed for negligence. The Chicago Tribune reports in 1890 that the average boiler operator earns $2.50 per day and works 6 days per week. Factory foremen, paid on production bonuses, routinely pressure operators to keep steam up regardless of conditions. One documented case from a Pennsylvania mill shows an operator fired after reducing pressure during a water supply interruption, the exact action that likely prevented an explosion. The knowledge gap kills in predictable ways. Operators mistake scale buildup in water glasses for safe levels, not understanding that the mineral crust blocks the true reading. They hear banging inside the shell and assume it's normal thermal expansion. They watch safety valves, weeping steam, and pack them with rags to stop the leak. These aren't acts of stupidity. These are decisions made by men working with partial information in an environment where caution costs jobs and boldness keeps families fed. The safety valve represents engineering's answer to human greed, and it fails almost immediately. The principle is elegant. A spring-loaded valve set to open automatically when pressure exceeds the boiler's rated capacity, bleeding excess steam before the shell ruptures. Massachusetts law in 1907 mandates safety valves on every boiler, calibrated to release at least 15 pounds below maximum working pressure. The valve is supposed to be the final line of defense, the mechanism that makes catastrophic failure impossible. In practice, it becomes the first thing factory managers tamper with. The methods vary, but the goal is identical. Some owners wire valves shut with steel cables, preventing them from opening at any pressure. Others file down the valve seat, creating gaps that let steam leak constantly at low pressure, convincing operators the valve is functioning when it's actually disabled. The most common modification involves adding extra weight to the valve's lever arm, forcing it to stay closed until pressure reaches levels 50 or 75 pounds above the boiler's design rating. Why would anyone deliberately sabotage the only device preventing an explosion? Because every pound of additional pressure means more power transferred to the factory floor, more machines running, more product manufactured per shift. Insurance company records from 1895 show that 62% of investigated boiler explosions involved safety valves that were either modified, disabled, or improperly maintained. The Hartford Steam Boiler Inspection and Insurance Company reports examining 4,471 boilers in 1896 and finding safety valve defects in 2,109 of them. That's nearly half. The numbers don't suggest carelessness. They suggest a system where safety mechanisms are treated as obstacles to profit rather than protection against death. Brockton, Massachusetts, knows shoe manufacturing, but March 20th in 1905 teaches it something else entirely. The R.B. Grover Shoe Factory employs hundreds of workers across 4 floors, most of them women operating stitching machines and presses. The building sits at the corner of Main and Kalmar Streets, a dense industrial corridor where factories pack shoulder to shoulder. At 7:45 in the morning, 3 stationary boilers in the basement explode simultaneously with a force that registers on seismographs in Boston 12 miles away. The blast vaporizes the boiler room, collapses the first floor into the crater, and sends upper floors pancaking downward. Workers on the 3rd and 4th levels fall through disintegrating floors into a pit of scalding steam, shattered brick, and twisted machinery. The building's north wall blows outward, showering the street with debris. Witnesses 3 blocks away describe a sound like artillery fire, followed by a rolling cloud of white steam that obscures the entire block. Rescue crews arrive within minutes, but can't approach for nearly an hour. The steam is too hot, the structure too unstable. When they finally enter, they find bodies stacked in stairwells where workers had rushed toward exits that no longer existed. Some victims are identified by jewelry, others are never identified at all. The final count reaches 58 dead and 117 injured, making it the deadliest boiler disaster in Massachusetts history. What could cause 3 separate boilers to fail at the same instant? The State Inspector of Boilers reveals a cascade of negligence. The boilers, installed in 1890, had never received professional inspection. Water treatment was non-existent, allowing scale buildup that reduced heat transfer and weakened the iron through overheating. Safety valves on all 3 units were found weighted beyond their design specs, set to release at pressures 40 pounds higher than the boiler's rated capacity. Most damning, the plant superintendent had been warned 4 months earlier by his own maintenance crew that the shells showed signs of bulging. He ordered the crew to stop mentioning it. The superintendent faces manslaughter charges but never serves time. The case drags through appeals and eventually settles with a civil penalty. Although his factory was insured, Captain Grover was financially ruined. The R.B. Grover Company declared bankruptcy and assigned its remaining assets, more than 30 Emerson shoe stores scattered around the country, to its creditors. The explosion kills instantly, but steam takes its time. Superheated steam at 200 degrees Fahrenheit doesn't behave like boiling water. It exists as an invisible gas carrying enormous thermal energy, and when it contacts human skin, it condenses instantly, releasing that energy directly into tissue. The result is burns that penetrate through multiple layers in seconds. Medical literature from the period describes these injuries with clinical precision. Third-degree burns covering 60, 70, sometimes 80% of the body surface. Skin peels away in sheets. Muscle tissue cooks. Survivors describe the sensation as liquid fire, a pain that doesn't fade but intensifies as nerve endings die and then regenerate. Dr. William Warren Potter, treating victims of the Park Hill shoe factory explosion in Haverhill, Massachusetts in 1898, documents the progression in the Boston Medical and Surgical Journal. Patients arrive conscious and speaking, their injuries not yet fully apparent beneath clothing. Within hours, the skin begins to separate. Fluid loss leads to shock. Infection sets in almost immediately, turning wounds septic before any meaningful healing can begin. Potter reports that of 23 patients admitted with severe steam burns, 19 die within 5 days. The survivors face months of recovery, multiple surgeries, and permanent disfigurement. Why does steam kill more effectively than flame? The answer lies in heat transfer. Steam carries roughly 5 times more energy per unit volume than hot air. When it contacts cooler skin, it releases that energy instantaneously while condensing back into water, which then continues to burn. Fire burns the surface and moves on. Steam penetrates and lingers. Hospital records from boiler explosion victims show recurring patterns. Many die not from the initial burns, but from secondary infections, pneumonia caused by inhaling superheated vapor, or kidney failure from the body's trauma response. The New York Times reports on December 13, 1902, that following the Abendroth brothers' boiler explosion in Port Chester, 8 men initially survived the blast, only to die over the following 2 weeks. Doctors had no effective treatment. Morphine managed pain. Saline solutions addressed fluid loss. Bandages stuck to melted tissue, causing additional trauma during changes. The medical profession of the era simply lacked tools to treat injuries this severe. Survival often came down to the percentage of body surface affected and whether the victim's lungs had been seared by inhaling steam. Everything else was suffering and time. Insurance companies start counting bodies because each one costs money. The Hartford Steam Boiler Inspection and Insurance Company, founded in 1866, becomes America's first systematic investigator of boiler failures. Their agents arrive at explosion sites with notebooks, cameras, and measuring tools, documenting everything from shell thickness to rivet spacing. What they discover isn't random mechanical failure. It's pattern. The same causes appear in report after report. Owners deferring maintenance to avoid shutdown costs, operators pressured to exceed rated capacity, safety valves deliberately compromised. By 1895, Hartford's chief engineer, Charles Pierce, testifies before the Massachusetts legislature that 90% of boiler explosions result from preventable human decisions rather than inherent equipment failure. The numbers tell a grim story. The National Board of Boiler and Pressure Vessel Inspectors, established in 1919 but compiling retroactive data, estimates that between 1880 and 1910, American boiler explosions kill approximately 2,000 people per year. That's one explosion killing or injuring someone every 4 hours, around the clock, for 3 decades. Individual incidents might claim 2 lives or 20, but the cumulative toll rivals major battle casualties without the public attention. State labor boards begin their own investigations. Ohio's Department of Factory Inspection reports in 1894 that of 3,847 boilers examined, 1,203 show defects serious enough to warrant immediate repair, and 87 are condemned outright as unsafe for any operation. Yet the department lacks authority to enforce shutdowns. Inspectors can recommend, they can warn, they cannot compel. Factory owners receive violation notices and continue operating, sometimes for years, until either repairs become economically necessary or the boiler explodes. What happens when evidence accumulates, but power structures refuse to act? Investigators compile devastating reports. They photograph bulging shells, corroded plates, and disabled safety mechanisms. They interview survivors who describe warnings ignored and concerns dismissed. They calculate that proper inspection and maintenance would cost factory owners roughly $200 per boiler annually. They also calculate that the average explosion costs $15,000 in property damage alone, not counting injury settlements or lost production. The data argues for regulation. Industry argues back. The American Boiler Manufacturers Association lobbies against inspection requirements, claiming they constitute government overreach and would drive up costs prohibitively. Meanwhile, the explosions continue at predictable intervals. The investigators keep writing reports. The pattern holds. Greenpoint. Brooklyn knows industrial noise, but nothing prepares workers for what erupts on an October morning in 1910. The American Manufacturing Company, the nation's largest producer of jute bagging for cotton bales, operates a sprawling factory complex covering 2 city blocks at Oak and West Streets. The boiler room sits in a 3-story corrugated iron building housing the steam plant that powers the entire operation. Chief Engineer Edward Corcoran arrives early, conducting his routine morning inspection. He finds everything in apparent working order. At his desk 100 feet away, his wife glances out the window and sees him sitting comfortably in his wooden chair, hands clasped behind his head, taking a brief rest. It's the last time anyone sees him alive. The explosion lifts a 40,000-pound boiler vertically through 3 floors and the roof. The massive cylinder becomes airborne, arcing over the factory yard before crashing into vacant ground near the riverfront several hundred yards from its moorings. The corrugated iron building disintegrates. The blast wave shatters windows throughout the complex and damages a frame building across the street. Workers in adjoining sections feel the floor shake and hear what sounds like artillery fire, then rush into the streets, unsure what happened. Steam pours from the wreckage, preventing rescuers from approaching for critical minutes. How does a boiler weighing 20 tons achieve flight? The physics are identical to rocket propulsion. When the shell ruptures catastrophically, pressure releases in a directional vector. If the break occurs at one end of the horizontal boiler and the structure is mounted vertically, the intact end becomes the nose of a projectile driven by escaping steam. The force is enormous. Hartford steam boiler investigators later calculate that the energy release equals several hundred pounds of dynamite detonating simultaneously. 6 men die, 5 instantly. Edward, Corcoran, and assistant engineer Dominic Permente, the only witnesses to the initial failure, perish in the blast. Fireman Andrew Doherty, laborer Patrick Walsh, and workers John McGee and Peter Peterson are killed by collapsing structure or scalding steam. 2 others suffer injuries so severe they're not expected to survive. The survivors can provide no information about what they saw or heard before the explosion. Consulting engineer: the bodies pile up faster than the laws can pass. Labor unions and reform groups demand government intervention throughout the 1890s, pointing to the mounting casualty figures as evidence that voluntary compliance fails. The American Federation of Labor submits testimony to Congress in 1902 documenting almost 1,500 boiler-related deaths over the previous 18 months. Factory owners counter that mandatory inspection would cripple American manufacturing, driving costs up and competitiveness down. The debate splits along predictable lines. Workers want protection, owners want autonomy, and legislators face pressure from both sides. Massachusetts becomes the testing ground. In 1907, the state passes the nation's first comprehensive boiler inspection law, requiring annual examinations by licensed inspectors and establishing minimum safety standards for construction and operation. Factory owners immediately challenge it in court, arguing the law violates property rights and constitutes unreasonable search. The Massachusetts Supreme Judicial Court upholds the statute in 1908, ruling that public safety supersedes private property concerns when the danger extends beyond factory walls. The decision creates a legal framework other states begin to copy, but implementation proves uneven. Ohio passes inspection requirements shortly after, then funds only 12 inspectors to cover more than 40,000 boilers statewide. Pennsylvania's 1915 law includes safety provisions, but grants inspectors no authority to force shutdowns, only to issue recommendations. Illinois establishes standards, but exempts boilers under 15 horsepower, a loophole that covers nearly a third of industrial units. The pattern repeats across industrial states. Laws with insufficient enforcement, requirements without consequences, standards undermined by industry-friendly exceptions. What's the real cost of delayed action? Between 1907, when Massachusetts passes its law, and 1920, when federal guidelines finally gain traction, an estimated 18,000 additional Americans die in boiler explosions. The National Safety Council, tracking industrial fatalities, reports that boiler incidents rank third among causes of workplace death, behind only mining disasters and construction falls. Newspapers fuel the debate with graphic coverage. The Chicago Tribune runs a front-page illustration after each major explosion, showing the blast radius and body count. The New York World publishes photographs of mangled boiler rooms alongside editorials demanding action. Public opinion shifts gradually toward regulation, but momentum builds only after each new catastrophe proves the reformers right. The legislative process moves at bureaucratic speed while the explosions maintain their steady rhythm. The electric motor arrives quietly and changes everything. General Electric and Westinghouse begin mass-producing industrial electric motors around 1910, offering factory owners an alternative to centralized steam power. The advantages are immediate. Individual machines can run independently, eliminating the complex belt and pulley systems that connect everything to a single boiler. Maintenance becomes simpler. Startup costs drop. Most importantly, electric motors don't explode. By 1915, new factory construction increasingly specifies electrical systems over steam, and the era of the massive stationary boiler begins its slow decline. Insurance accelerates the transition. The Hartford Steam Boiler Inspection and Insurance Company raises premiums on older boilers every year, making operation progressively more expensive. A factory running a 20-year-old boiler in 1920 pays triple the insurance rate of one using equipment less than 5 years old. The financial pressure pushes owners toward modernization, accomplishing through economics what regulation struggled to achieve through law. World War I's industrial mobilization speeds the process. The government demands maximum production for the war effort and provides loans for factory modernization. Steel becomes available for new boilers built to updated standards, and many owners replace aging equipment rather than repair it. The National Board reports that between 1917 and 1919, more than 8,000 pre-1900 boilers are retired from service, either scrapped or sold to smaller operations willing to accept the risk. But thousands remain. Smaller factories, particularly in the South and rural Midwest, continue operating steam systems well into the 20s and beyond. The economics make sense for operations that can't afford electrical infrastructure or that already own functional boilers. The Pemberton Mill in Laurel, Mississippi operates its original 1892 boiler until 1927. The Valley Cotton Mill in Roanoke, Alabama, runs steam power until 1931. These facilities maintain older technology not from preference but from necessity, accepting higher insurance costs and regulatory scrutiny as the price of staying in business. The final major stationary boiler explosion occurs on April 23, 1932, at the Standard Underwear Company in Bristol, Tennessee. The boiler, installed in 1897, ruptures during the afternoon shift, killing 3 workers and injuring 11. Investigation reveals the familiar pattern: corroded shell, modified safety valve, pressure exceeding design limits by 60 pounds. Even at the end, even after decades of regulation and technological alternatives, the fundamental dynamic remains unchanged. Push it too hard. Ignore the warnings. Pay the price. The final accounting takes decades to compile, and the numbers remain incomplete. Researchers estimate that between 1865 and 1940, stationary boiler explosions killed at least 50,000 American workers and injured more than 200,000 others. The true figures likely run higher, as many incidents in smaller factories went unreported or were classified as industrial accidents without specifying the cause. What's documented beyond dispute is the pattern: preventable failures, repeated warnings, and a system that prioritized production over human life until the cost became impossible to ignore. But those boiler rooms left something behind besides casualty statistics. The regulatory framework born from this era shapes workplace safety to the present day. The American Society of Mechanical Engineers publishes its first boiler and pressure vessel code in 1914, establishing construction standards that become legally binding in most states by 1925. The National Board of Boiler and Pressure Vessel Inspectors, formed in 1919, creates a standardized inspection system and inspector certification process that spreads nationwide. These organizations still exist, still set standards, their authority tracing directly back to the explosion era. The legal principle matters even more. Courts in the early 1900s established that employers cannot prioritize profit over worker safety, that the right to operate a business does not include the right to create lethal working conditions. This precedent becomes foundational to the Occupational Safety and Health Act of 1970, which creates OSHA and makes workplace safety a federal mandate. The connection runs straight from those boiler room disasters to modern safety regulations protecting millions of American workers. Individual tragedies fade, but their lessons compound. The Grinnell disaster leads to Massachusetts inspection laws. The Cleveland explosion pushes Ohio toward regulation. Bristol's 1932 incident, one of the last, prompts Tennessee to finally adopt comprehensive boiler codes. Each explosion adds pressure, literal and political, until the system changes. We end where we began, in that moment when the gauge needle climbs past red and an operator reaches for a valve that won't move. But now we understand every decision that led there, every warning ignored, every safety measure defeated by the calculus of profit. The massive stationary boilers are gone, retired to scrap yards and industrial museums. What remains is the knowledge, bought with blood and written into law, that some risks cannot be justified and some pressures must never be allowed to build.